11 review. Number 1. The RMS error of the regression line for predicting y from x is v, or 5. Right, you take the SDY and you multiply it by the square root of 1 minus r squared. What effect does that have on the SDY? What happens when we multiply the SDY by the square root of 1 minus r squared? The SDY becomes the RMS error, and how do those two numbers compare? The RMS error is smaller. Unless, of course, r is 0, then they're the same size. Or if r is 1, then the RMS error would be 0, because the line is perfect. Okay, number 2. A computer program is developed to predict the GPA of college freshmen from their high school GPAs. The program is tried out on a class whose college GPAs are known. The RMS error is 3.12. Is anything wrong? Yes, something is wrong. Why? Way too big. So if we did, so if I had high school GPA and college GPA, we would expect kids who do well, who have a high GPA in high school, would have a high GPA in college. Right? We would expect the line to go up, not down. Right? If you do terrible in high school, does that mean you're going to do really well in college? Yeah, probably not. Now, it's probably not a very good football, because GPAs can be all over the place, right? Maybe you just didn't like high school, or maybe you love high school and college isn't for you. So, what does the RMS error tell me about this football? And my lines, that's the SD line, isn't it? So here's the regression line. What does the RMS error tell me about the regression line? So how far on average are the points away from the regression? So the RMS error, if I draw it like this is 1 RMS, and that should capture 68% of the people. Okay? There's another definition of the RMS error, and that is the RMS error is the SD of every column. You remember that? So it's how far away from the regression line we need to go to capture 68% of the people, which is basically the SD of the regression line, and at the same time, it is the SD of every column. So what's wrong with having an RMS error that's equal to 3.12? Well, that gives us a span of 6.24 GPA points, right? How many people does that capture? Everybody. And a whole bunch of people that don't exist. Because this scale maxes out at 4, and this one also maxes out at 4. So that RMS error cannot possibly be correct. Oh, no. No, the number itself is just impossible. Okay, number 3. Tuddenham and Snyder obtained the following results from 66 California boys aged 6 and 18. So we have average heights and SDs with an R value. The RMS error for the regression prediction of height at 18 from the prediction of 18 from 6. So how are we going to find the RMS error? We have a whole bunch of information. What do I use to find the RMS error for predicting 18 using 6? So I need the R value, the square root of 1 minus 0.8 squared, times the SD of Y. How come Y? Because I am predicting Y. I'm using an X value of age 6 to predict 18. So I'm going to times that by 2.5. And I get error. What did I do wrong? Oh, 0.8. There we go. 1.5. And notice that is smaller than the SDY. What if R gets bigger? So what's that equals 1.5. What if 0.8 gets bigger? What's going to happen to 1.5? It's going to get smaller. Why? Well, right now I have a pretty narrow football, right? And if I change that to 0.9, then I'm going to have an even narrower football. And what happens to the RMS error as the football becomes narrower? It gets smaller because to capture 68% of the people, I don't need to go up and down very much to do so. All right? If this number goes down, which will make it more of a rugby ball, what happens to my RMS error? It goes up because I need to have more, I need to have a larger distance to capture the same number of points. Okay. And B, find the RMS error for the regression prediction of height at 6 from 18. What do we do there? Same thing, except instead of 2.5, I'm going to do 1.7. So I'll just do the previous equation and change it to 1.7. And I get 1.02. Why is this RMS error smaller than the other RMS error? Because the x's are less spread out than the y's. So if I go to my original graph, right, the variation of x's, the distance to do one SD, is smaller than the distance to do one SD on the y's. The x's are less spread out than the y's. Why would the 6-year-old measurements be smaller than the, or sorry, not smaller, have less spread than the 18-year-old measurements? Because the 18-year-olds are a whole lot taller. And so the distance, the spread between the shortest 18-year-old and the tallest 18-year-old is going to be a lot more than the distance between the smallest 6-year-old and the tallest 6-year-old. Okay. 4. A statistical analysis was made of the midterm and final score in a large course with the following results. The scatter diagram is football shaped. For each student, the final score was predicted from the midterm score using the regression line. A. For about 1/3 of the students, the prediction for the final score was off by more than blank points. So I have football shaped, I have a regression line. My point of averages is 50 for the midterm and 55 for the final. Oh, that's good news. What happened? People learned something. That's a bonus. Okay. The average, or the SD here is 25, and the SD here is 15. Oh, that's bad news for some people. That's bad news for the people who did really, really well on the midterm. But it's also good news for the people that did really poorly on the midterm, because the final had less spread than the midterm did. And the midterm was lower than the final, so that's also good news. Okay? So, A, for about 1/3 of the students, the prediction for the final score was off by more than blank points. What is that saying? Well, this line takes midterm and predicts final. Right? So, let's pick a person specifically. This person here. So we'll say that's 55, 60. So this person who scored 55 points on the midterm scored 60 on the final, which was more than, well, let's do 68, which was more than they expected to earn. If you look at the class on average, that person was only expected to earn that much instead of 68. So that person was higher than expected. Likewise, this person was lower than expected. Now, where are the people expected to land? 2/3 of them are expected to land within one RMS error. So 1/3 of the people are split between those two pieces of that Easter egg. Look at that, beautiful. So 1/3 of the people were more than one RMS error away from the predicted Y value. So the answer to A is simply the RMS error using the Y's. So I take the square root of 1 minus 0.6 times my SDY of 15. Oh, don't forget to square it. If you don't square it, it won't work. Nope, that won't work either. 12. Is that what you guys got? 12? Okay, B. Predict the final score for a student whose midterm score was 80. Okay. So, I want to know if I score 80, what is my predicted score? Well, how far is it from 50 to 80? 30 points. Okay, what do I do with 30? Divided by 25, which gives me a z-score. 1.2. Exactly, correct? I think it's exact 1/5, right? 1 and 1/5. So 1.2. What does 1.2 tell me? That's how many SDs this person is above average. So how do we find the Y value? I go up 1.2 SDYs. So 1.2 times the SDY times R. So 1.2 times 15 times 0.6. And that cuts this down to 10.8. And that is points on the test. What do I do with 10.8? I have to add it to the Y bar, 55, so I get 65.8. Does that seem reasonable? Yes. Why? Because of the regression effect, it's less than 80, but it's a lot less than 80, isn't it? Why is it a lot less than 80? Oh, well, the SD did affect it, but mostly it's the R value. That R value is not very strong. And that's what brings it down. But you're right, the SD does bring it down too, because the SDY is smaller. Okay. This prediction is likely to be off by how much? 12. I didn't do any calculations. Where did I get the 12 from? That's the RMS error. So what that means is this column right here has an SD of 12, which is the RMS error. The SD of all of the Y values is 15, but the SD of the column is the RMS error of 12. Okay, 5. Use the dating exercise 4 to answer the following questions. About what percentage of students scored over 80 on the final? Well, I know the predicted value. Is that going to help me? No, because it says 80 on the final. So how do I do that? We don't expect a lot of people, right? How do I figure it out? I need to find a z-score in the histogram for the y values. So this graph doesn't do me any good. So I need to draw my histogram. My average is 55, and my SD is 15. And I want to know 80 and which direction? To the right. So I want all of that. And the pattern is 80 minus 55 is 25. Divide that by 15. 25 divided by 15 gives me a z-score. Z equals 1.6 repeating. Now what? Shade norm. So we shade norm from 1.6 to 5. So we want to go from 1.6 all the way out to infinity, but eventually there's so little area over there that we just quit caring. So I could say 1.6 to 1,000, and what we realized early in the school year is once you get past 5, the calculator, the numbers are so small the calculator doesn't pick it up. So if well, let me push this. Oh, my window's really weird, but whatever. Oh, I better fix that so you guys can see it. So zoom recall, and then I need to redo my shade norm. And I get 0.47. So I'm going to say 4.8%. Okay. Now, if I did shade norm from 1.66 to 4, then I might get something like 4.7. But if I do 1.66 to 6, I get this number again exactly. So once you get beyond 5, there's so little area out there that you can't tell the difference. So it doesn't really matter what number you pick as long as it's 5 or bigger. And we skipped B. Explain your answers. Well, this is the explanation, right? 6. In a study of high school students, a positive correlation was found between hours spent per week doing homework and scores on standardized achievement tests. The investigators concluded that doing homework helps prepare students for the test. Do the conclusions follow from the data? Are we allowed to say homework helps students take tests? No. Why not? It's an observation. Do we suspect that's true? Probably. What else could be happening? Okay, that could be it. Or the people who are good at taking tests are also good at getting their homework done. Right? That could be an explanation. Maybe some sort of brainwashing. I don't know. There are lots of different answers. But do we suspect that homework helps people take tests better? Yes. But you would have to do a study. Right? You'd have to give a bunch of kids, here's a bunch of homework. You guys do it, you guys don't do it, and then after the homework is done, have everybody take the test and see what happens. Now that's not terribly unethical, unless, it's somebody's grade, right? If you say, oh, you failed the test, you didn't do the homework, but you failed the test, you get an F. That's not ethical. Yeah. All right, 7. The freshmen at a large university are required to take a battery of aptitude tests. Students who score high on the mathematics test also tend to score high on the physics test. On both tests, the average score is 60. The SDs are the same too. The scatter diagram is football-shaped. Of the students who scored about 75 on the math test, then just about half scored over 75 on the physics test, more than half scored over 75 on the physics test, or less than half scored over 75 on the physics test. 3. Why? The regression effect. So for those people who scored 75 on the first one, we would expect the average of the other one to be lower. So that would be 3.